Welcome back. The next theorem that we are going to see is if function is continuous on the closed interval a b, then the function is RS integrable for some suitably monotonic function. This alpha is monotonically increasing function. You just have that in your mind. So if we wish to rewrite this statement, we shall have this as, in a simpler way, continuous functions on any closed interval is RS integrable on the same closed interval AB. In a simpler notation, we shall write like this. Okay, let us get into the technical proof of this. Initially, let us take epsilon as some given quantity, given positive quantity, and we'll have to choose some eta in a way that alpha of beta minus alpha of a multiplied with this eta is less than epsilon. We are choosing eta in this way, right? In simpler notation, we have to choose eta less than epsilon upon alpha of beta minus alpha of a, and this eta is a positive quantity. How do we get this guarantee? Epsilon is a positive quantity. Since alpha is monotonically increasing and b is bigger than a, this tells us that alpha of beta minus alpha of a is bigger than 0. So this is a positive quantity and epsilon is also a positive quantity. Hence, eta has to be a positive quantity. We are choosing eta in this way. And we mark this as equation 1. Let me write this here. Eta is less than epsilon upon alpha of beta minus alpha of a. This quantity, we are taking some quantity like this and our eta has to be smaller than this. Now we are choosing a partition and this delta xi minus this is what we take it as epsilon. Okay, whatever may be the epsilon be the case, let us take this to be our epsilon, and absolute of mi minus mi is less than eta here. Do you think this absolute sign is absolutely needed? No, because supremum of, okay, we know that this mi, okay, let me write here, mi is the supremum of f of x in the interval subinterval ii, and mi is the infimum of f of x in the subinterval ii. This ii is what? Xi minus 1 comma xi. Okay, so supremum, infimum is always smaller than or equals supremum, right? This tells me that supremum quantity minus infimum quantity has to be always non-negative. So whether we have this absolute sign or not, it doesn't bother. We take this as equation 2. Now we'll consider, okay, I think you people can understand this thing, that is why I'm just erasing it. If you want, let me write I to be the xi minus 1 comma xi. Okay, then we consider this one. By definition, what is UPF alpha? That is summation I runs from 1 to n, supremum of fi multiplied with delta alpha I. And for LPF alpha, it is the infimum quantity. Right? We are done with this. We just combine things up. By our assumption, this quantity is less than eta. So this is less than eta multiplied with summation I runs from 1 to n alpha of xi minus alpha of x I minus 1. When you start with the I is equal to 1, what are you going to get? Alpha of 1 minus alpha of 0 plus alpha of 2 minus alpha of 1 plus alpha of 3. Sorry, I have, sorry. So it is x1, x0, x2, x1, x3, x2, and at the last what are we going to have? Alpha xn minus alpha xn minus 1. If you notice here, your x1 get cancelled, x2 gets cancelled, alpha 3. In this way, all terms will get cancelled, and finally you will be left with what, only two terms, that is alpha of xn minus alpha of x naught. Usually alpha of xn is what, your b, and x naught is what, a. So this is going to be eta multiplied with alpha of beta minus alpha of a, and we have chosen eta in such a way that when you multiply eta with this quantity, this is less than epsilon. So we have less than epsilon, and that is by our equation 1. This tells us that UP f alpha minus LP f alpha is less than epsilon. Now, by the necessary and sufficient condition, by the necessary and sufficient condition of Riemann RS integrability, we shall conclude this theorem. We get f is Riemann Celsius integrable, and this completes the proof. Thank you.